All right, we are on page 42, friction and gravity. No homework questions tonight. No videos other than this, so, you know, if you don't watch this, just read. All right, here we go. Talk about what happens when you jump on a sled on the side of a snow-covered hill. You can predict that that sled is probably going to take off down the hill, right? But what's going to happen when it gets to the bottom of the hill?
It's going to just keep going.
It's going to come to a stop. It's going to go for a little ways, but then it's going to come to a stop, you know, providing the fact that you don't hit a tree or somebody else going down the hill. You know, it's going to come to a stop. And the reason being is because that sled will change motion on the side of the hill, and then again at the bottom. In each case is an unbalanced force that acts on the sled. The force of gravity causes the sled to accelerate down the hill, and then the force of friction is what slows it down. Even though it's going down a smooth surface sometimes that is slick, gravity is still, gravity is there, but then friction is also still coming into play. Okay? There is still friction there. Okay? And friction, of course, is when the sled moves across the snow, the bottom of the sled rubs against the surface of the snow. In the same way that the skin of they talk about a firefighter sliding down his brass pole in the firehouse, you know. It's slick. They've got it all polished up so that they can slide down that thing, but there is still friction between his hand and that pole.
I feel like that would hurt.
Okay,
That would
there's still friction between the hand and
The,
pole. Well, you'll see a picture over on page 43.
Look at the set.
That's actually a close-up picture of
I really like
that polished pole. So it does. It has a little bit of a coarseness to it. You can't necessarily feel it, but it is there. It's microscopic, but that does create the friction. Okay. So when the force of two surfaces exerted on each other when they rub against each other is, of course, friction. Yes, Bryson?
Can't you see germs with a microscope?
You can. You can see all kinds of neat stuff with a microscope. You can. Okay? In general, smooth surfaces produce less friction than rough surfaces, obviously. Okay? The strength of the force of friction depends on two factors: how hard the surface are pushing against each other, and the type of surface that is involved. Okay? If you're trying to push something across a rough concrete, it's harder than it is if you're trying to push it across a glass top of something. You know, obviously, it's going to be still going to have friction, but you're going to have more friction with the trying to go over a concrete surface. Okay. And that picture up there, it's got those reindeer pulling those two guys. I love the tongue hanging out of those poor things.
My dog.
Yeah, they've been at it for a while. But you notice how the direction of motion is going one way, and friction force is applied the opposite direction. Okay, so that's the thing you got to remember about friction. If you're going this way, if you're pushing something that way, friction is working against you. It's going the opposite direction. Okay. That's why there's friction. Otherwise, everything would just be going nice and smooth. Okay? A snow-packed surface or a metal firehouse pole may seem quite smooth, but you see the figure right there on figure 5 on page 43. Again, that is why there is friction there. Okay? Let's see. And then you get into the 4 types of friction. Okay, you've got static. You got the friction that acts on an object that are not moving is called static friction. Okay, your desk right now is just sitting there. It has static friction. Okay, if you decide to push that desk, which most of you will, because I walked in this morning and they were sitting here. Don't do that. If you had any idea how much that irritated me.
The cleaning people.
It
might be the cleaning people.
Well, it is. I'm sure it's part of it. Anyhow, But static is you have to overcome something sitting still to get it to move. Okay, that's the static. It shows you a picture there on page 45 of the guy pushing against a sled. Okay, so to make the sled move, the athlete first has to overcome the force of static friction, and static friction acts on the opposite direction to the intended motion. I mean, all friction does. But static is when you've got to overcome to get it to start moving. Okay, you've got to overcome the static friction. If you push on the desk with a force less than the force of static friction between the desk and the floor, the desk will not move. To make the desk move, you have to exert a force greater than the force of static friction.
So,
Once the desk is moving, you no longer have the static friction, but now you're overcoming the sliding friction. Okay, you got it moving. Yes, Caleb.
If there was more friction than there was motion, isn't that what causes, like in a car to go reverse? Is there's more
mean a hydroplane?
friction than there is motion? Or how does that work?
No, your car backs up because the transmission is put in reverse and it backs up. It makes the tires go the other way.
It's still basically moving, like it's moving.
I think he's
Well,
trying
the
to
car,
say-
from the way you look at it, it's not moving forward. But technically, it is still doing the same thing as it is. Like the car's still
We're
doing
not talking
what it
about cars.
was.
We're not talking about what makes a car work. That's not what we're talking about today. That's not what we're talking about. And that has nothing to do, friction is not making that car back up or go forward. That's not, it overcomes friction to move, but that's not why the car moves. That's the engine, the powertrain, the transmission, there's a lot of things, okay? That's not what we're discussing today, though. Sliding friction. Sliding friction occurs when two solid surfaces slides over each other. Okay? Sliding friction can be useful. For example, if you spread sand on an icy path to improve your footing. Ballet dancers applies a sticky powder to the soles of their ballet slippers so they won't slide and slip on the dance floor. When you stop your bicycle using the handbrake, you got those little rubber pads that closes in on the tire, okay? And that's what the friction there causes that tire to slow down and eventually stop, okay? On the other hand, if you're out running across the basketball court and you lose your footing and you fall down, you also create friction between your hands and your knees and the pavement, and usually your skin loses that battle and you come up all skin up, okay? But that is friction that causes that burn on your hand there, losing the skin, okay? Then you've got rolling friction. When an object rolls across a surface, rolling friction occurs, okay? That is easier to overcome than sliding friction for similar materials. This type of friction is important to engineers who design certain products. For example, skates, skateboards, bicycles need wheels that move freely. So an engineer uses ball bearings to reduce the friction between the wheels and the rest of the product. And these ball bearings are small, smooth steel balls that reduces the friction by rolling between the moving parts. Okay? You can, it shows you over on page 44, it talks about if you took basically two plates and you put them on each other and you try to spin one of them, it doesn't spin real well. But if you put marbles in one and then set the other plate on top of it, and it's going to spin, it's going to turn. Okay? If you ever notice in your microwave, the thing that turn, take a look at it. It's got wheels. Wheels there. Okay? It doesn't just sit there and start spinning. Okay? It's got wheels and it's got a motor underneath it that causes that thing to move, and then that rolls around those wheels.
And it makes it.
And that's what makes it move. Okay? And it overcomes the friction. So you have a rolling friction there, and it's easier for that thing to move when you put something on it. Okay? All right. Fluid friction, such as water, oil, or air, are materials that flows easily. Fluid friction occurs when a solid object moves through a fluid. Like rolling friction, fluid friction is easier to overcome than sliding friction, obviously. And this is one of the parts of the machines that must slide over each other are often bathed in oil. Okay? And this way, the solid parts move through the fluid instead of sliding against each other. When you ride a bike, fluid friction occurs between you and the air. Cyclists often wears a streamlined helmet, specially designed clothing to reduce fluid friction, okay? That's why you see the serious bikers are in their spandex clothing, and they have their helmet that is shaped to, so when they have their heads down, the wind resistant goes over their head, things like that. That's why your car engine, you want to talk about a car, that's why the pistons that goes up and down that generates the energy. That's why you have to have your oil changed on a regular basis, because and check to make sure it has the proper amount of oil, because it goes down into the oil pan, and then it has an oil pump that brings it up, and it lubricates those pistons. If it didn't, the friction between that would get so hot that it would actually do damage to your motor. Okay, that's why if you ever, when you get old enough to drive, your engine light ever comes up or your oil light comes up, don't keep going, oh, that's no big deal, okay? Because it could be the fact that you're low on oil and your engine would actually seize up and not work, because it's not, that friction gets so hot that it will actually start to weld it together almost. Okay? All right, gravity. Would you be surprised if you let go of a pen that you were holding and it did not fall?
Yes.
Yeah, that would surprise most of us. We just kind of hung in the air or went floating off somewhere. That would kind of, we would all be going, wow, what happened? Okay.
Tie a fishing line to it.
Ta-da!
There goes.
Well, we kind of meant without a trick. We kind of mean.
Well, a piece of string.
Okay. So, you are so used to objects falling that you may not have thought about why they fall. Of course you have, because you're smart children. But one person that thought about it, of course, was Isaac Newton, who watches an apple. Supposedly the story has it that he watched an apple fall off of a tree, and he went, there is a force that causes that. You know? Someone like myself, I would just looked at it and went, wow, now it's easier to eat the apple. It's on the ground. I don't have to climb the tree. But, smart people goes, wonder why that happened. And so he creates math to figure it out. Well, he didn't create math. He another type of math there. Anyhow, but he starts playing with the idea, and he kind of discovers gravity. He didn't invent gravity, but he did discover gravity and put it into terms that people can kind of understand, okay? He also realized that gravity acts everywhere in the universe, not just on Earth. It is the force that makes an apple fall to the ground. It's the force that keeps the moon orbiting around the Earth. The force that keeps all the planets in our solar system orbiting around the sun. What Newton realized is now called the law of universal gravitation. The law of universal gravitation states that the force of gravity acts between all objects in the universe. And this means that any two objects in the universe, without exception, attracts each other. You are attracted not only to Earth, but also to all the other objects around you. Earth and the objects around you are attracted to you as well. However, you do not notice the attraction among objects because the forces are small compared to the force of the Earth's attraction on you. Okay? That's just like we talked about in astronomy. The reason we're not going floating off somewhere is because the Earth's gravity is so strong it pulls us down. But as we pull down on as the Earth pulls down on us, we pull up on the Earth. But because we are nowhere near the size of the Earth, we don't have the mass or anything, we make absolutely no impact as far as moving the earth. Yes?
Can I go to two people?
Me. I'm looking at pictures. Bobby.
You got people come in, you got to interview people now. You know, heaven forbid that we could just teach. All right. Hey, that's over. You didn't get picked. Whine somewhere else. Pay attention to class.
Yes, sir.
Okay? All right. Factors affecting gravity. 2 factors affects the gravitational attraction between objects, mass and distance. Mass is measured in the amount of matter in an object. The SI unit of mass is kilograms. 1 kilogram is the mass of about 400 pennies. Okay, so if you ever picked up 400 pennies, it's got a little bit of weight to it. So a kilogram, it's got a little bit of weight there. Okay? Everything that has mass is made up of matter. The more mass an object has, the greater its gravitational force. Because the sun's mass is so great, it exerts a larger gravitational force on the planets. Of course, that's why the planet stays in orbit around the sun. In addition to mass, gravitational force depends on the distance between the objects. The further apart 2 objects are, the less the gravitational force is between them. Okay? For a spacecraft leaving Earth and traveling to Mars, the gravitational pull from Earth is pretty high until it gets to a certain distance. As it's going away, it is decreasing. The gravitational Earth pull is decreasing. And as it gets closer to Mars, then Mars's gravitational pull is actually stronger on that spacecraft than it would be, than Earth's pull would be at that point in time. Okay? Yes, sir?
Isn't like water? Isn't it like a liquid because it has like not much mass? Isn't that what causes fluids?
Actually, it's a liquid simply because the molecules are spread out enough that it can pass each other. That's what makes it a liquid. But in a solid, the molecules are really close together and they're moving all the time, but they're so close together they can't pass each other. So that's what makes it a solid. Liquids are spread out a little bit more where they can bump into each other and actually pass each other. That makes it a fluid. Okay?
And like the more denser it is with the molecules, the more mass it has.
Mm-hmm. Yeah, very good. Yeah. The more dense something is, the more mass it has. Very good. Okay? Mass is sometimes confused with weight. Mass is measured in the amount of matter in an object. Weight is a measurement of gravitational force exerted on an object. Okay? And the force of gravity on a person or object on the surface of the planet is known as weight. Okay? So when you weigh yourself, when you step on a scale, it's actually the Earth's gravitational pull is pulling down on you, and that scale is telling you how much it's pulling down. Okay? And that's how you figure your weight. But the mass of something never changes, okay? If I took a 16-pound bowling ball from Earth, okay, I weigh it, it's 16 pounds, and I took it to the moon, and I weighed it on the moon, no, let's say it weighed 2 pounds, okay? Let's say it weighed 2 pounds. But the ball itself didn't change. The mass did not change. That makeup of that ball is the exact same as it was on Earth. What changes is the amount of gravitational pull. Okay? The moon does not pull down as hard as the Earth, so it weighs less. If I brought it back to Earth, it's going to weigh 16 pounds again, and again, it's still going to be the exact same ball. The mass, the makeup and everything of that ball never changes. Okay? It's the gravitational pull that makes it weigh more or less. Okay? I love this down here where it shows you the astronauts in spacesuits. On Earth, that thing weighs 1,617 newtons. And on the moon, it weighs 270 newtons. That's quite a bit of difference there.
Wait, how much pounds are there? Like 50?
Quite a bit of difference.
tell me
I don't know, do the math and figure out what a Newton is.
I'm too lazy.
Let me know tomorrow.
I'm too lazy to do it.
Uh-huh. All right.
I don't know how to do it.
All right, gravity in motion. Well, just remember, gravity is 9.8 meters per second square. Okay. All right, on Earth, gravity is a downward force that affects all objects. You hold a book, you exert a force that balances that book, okay? So gravity is pulling this book down. I'm exerting a force that is holding this book up. If I move my hands, I'm going to have to bend down and pick my book up because gravity is going to win. It's going to take the book to the floor, okay? It's not just going to float
What is
up
the
here.
floor
Okay?
Inertia.
When the only force acting on an object is gravity, then the object is said to be in free fall. Okay? An object in free fall is accelerating. So, in a free fall, the force of gravity is an unbalanced force which causes the object to accelerate. But remember, what's taking place?
Air resistance.
Air resistance is going to start to come into play. Okay? Even in a free fall, air resistance is going to come into play. And what happens when it hits a certain speed? What do we call that?
Oh, I can't remember.
Okay. Velocity. Terminal velocity. Okay. How much object accelerates as they fall near the surface of the Earth? The acceleration due to gravity is 9.8 meters per second square. That is why, remember when we did our little experiment in astronomy where I dropped the two different sized balls and things and they hit the ground at the same time because they had different weights, but they hit the ground at the same time? That's because the gravity pulls down at 9.8 meters per second square. It doesn't matter the weight of the atom. The pull is the exact same. That's one that hit the floor at the same time. Okay? Yes?
But then I see what you're saying. But then how, like a tissue, if you drop that or
That's
a piece
air
of paper-
resistant. That's air resistance hitting it. If you drop, same thing with a piece of paper. If you remember, we took a piece of paper, we dropped the ball on a piece of paper,
Oh,
and the
yeah.
ball hit the ground and the paper just floated down. Okay? But if you take that piece of paper and wadded it up, crumpled it all up,
It would work.
it hits the ground at the same time.
Imagine if water was there.
Okay? But that's a good question. That is air resistant though.
That was actually kind of sick. Because if you just.
All right, so if starting velocity is 0 meters per second, after 1 second, its velocity would have increased to 9.8 meters per second. After 2 seconds, the velocity is 19.6 meters per second. That's 9.8 plus 9.8, okay? So every second, it increases 9.8 meters per second in velocity, okay? Remember the airplane taking off the other day when we talked about that? How it started at 0, then it went to 8, and 16, and over a 5-second period of time, it had gotten up to 40. Remember that? Some of you do, some of you don't. Okay. Okay, while it may seem hard to believe at first, all objects in free fall accelerate at the same rate regardless of their mass. Okay, and that's back again. If I jumped out of an airplane and Macy jumped out of an airplane and we jumped out at the same time, we're going to fall together, even though I outweigh her by 100 pounds. Okay, we're going to fall together. Okay, until I get chicken and pull my shoe. Okay.
Wait,
Yes, sir.
how far do you have to be to pull your shoe? Have you ever done that?
I've never free fallen like
I
that.
would have free fell.
Everything I've done, I mean, I got 126 jumps, but they all with a stat line. So,
If I'm ever like have a
Okay.
leap belief,
All right.
I'm still jump off.
air resistant. Despite the fact that all objects are supposed to fall at the same rate, you know that this is not always the case. For example, the oak leaf flutters slowly to the ground. This is back to what Leo was asking about just a second ago. While an acorn drops straight down. Okay, so objects falling through air experience a type of fluid friction called air resistant. Remember that friction is the direction opposite to motion. So air resistance is an upward force exerting on falling objects. Air resistance is not the same for all objects. Falling objects with a greater surface, I mean, think about it. If you dropped a sticky note and a regular sized piece of notebook paper, that notebook paper is going to get more air resistant than a sticky note because there's more surface area to it. Okay, you understand? Yeah. Yes, Caleb.
So, it doesn't have to be the exact same surface for it to be like, for it to fall, to hit the ground at the same time. Like you said, there was the piece of paper that was crumbled up and then something.
Yeah, as long as you crumbled it up, it fell at the same rate
I
as
think I
a
know
baseball.
why. I think I know why.
Yeah, it just doesn't, so if it's too much of a difference, it won't fall, it won't touch the ground at the same time. But if it's just a little bit of a difference, it's still.
No, actually, it will touch. It will hit the ground at the same time.
So 100 pounds.
100 pounds hit the ground at the same time as 2 pounds if you drop them from the same.
No, I'm saying if you had,
For 1,000,000 pounds.
if you had like a piece of paper and then,
Not skydiving.
a rock,
Miller, first
and,
the paper would fall out.
yeah, but what I'm saying,
No, the paper has more air resistance.
Okay, now, if you drop just a sheet of paper, air resistance keeps it from falling. Okay? But if I take that sheet of paper and I wad it up and I make it into a ball, it will drop at the same time the rock.
yeah, that's not what I was saying. I'm saying, does it have to be a significant amount of
No.
difference in the surface?
You're talking for air resistance?
No, surface. You said like each object has this like surface.
I was
you
talking
know?
about paper when I'm talking about surface.
Yeah, and I'm saying.
I'll tell you what, let's get back to it. Let's finish up, and then you and I will have that conversation. All right, let's finish up class, and then you and I, because I want you to try to understand what you're saying a little bit better, and see if I can give you an answer to that. Okay? Air resistance increases to velocity as a falling object speeds up. The force of air resistance becomes greater and greater. Eventually, a falling object will fall fast enough that the upward force of air resistance becomes equal to the downward force of gravity acting on the object. Okay, remember the guy coming out of the airplane free falling, he will hit a max speed of about 122 miles per hour, and then that is considered terminal velocity. He is as fast as he's going to go because air resistance kicks in at that point in time. And that he will not get any faster than about 122 miles an hour, which in my opinion is plenty fast enough when you're falling through the air. Okay? Projectile motion. This is something we can try tomorrow too. This will be interesting. Rather than dropping a ball straight down, what happens if you throw it horizontally? An object that is thrown is called a projection or a projectile. When a projectile is thrown horizontally, it lands on the ground at the same time as an object that is dropped. I've never done that experiment. We'll have to try that tomorrow. Okay? The yellow ball was given a horizontal push at the same time as the red ball. That doesn't mean that if I take it and I throw it across the room and I drop one here, that ball is going to go all the way across the room and fall before this one does, or at the same time as this one. It means as I drop it, we knock it off the desk just a little bit and it comes off. It's still going to hit the ground at the same time. Okay, that's the projectile. We're not talking me throwing it 100 yards down the field, okay? So in similar ways, an arrow flying towards a target is a projectile. Because the force of gravity, the arrow will fall as it flies towards the target. So if you try to hit the bullseye, you must aim above it to account for gravitational pull. When you throw a projectile at an upward angle, the force of gravity reduces its vertical velocity. Okay? So if any of you have ever shot bow and arrows, you know if you're shooting from a long distance, you aim a little high because as it's going through the air, gravity is pulling it down. Okay? All right, so we'll pick up there tomorrow. Long video today.